Let's subscribe,
like, share, and leave the comments.
And now, let us perform an experiment to observe the energy changes during change of state. We take some ice cubes in a beaker and suspend a thermometer into the ice cubes. We note the temperature. It's 0 degrees Celsius. Heat the ice cubes and record the temperature after every minute. Keep stirring the ice-water mixture constantly so that the temperature is uniform throughout. We observe that the temperature remains constant at 0 degrees Celsius even though heat is being supplied. The temperature remains constant until all the ice melts to water at 0 degrees Celsius. Continue heating the water. We observe that the temperature is increasing. Record the temperature until the water starts boiling. Continue heating. The boiling water is converted to steam. We observe that the thermometer reading remains constant at 100 degrees Celsius, which is the boiling point of water. So we see that the temperature remains constant whenever there is a change of state. The heat energy supplied at this point is used to break the forces of attraction between the water molecules, and therefore there is no change in temperature. The amount of heat energy required to change a certain amount of solid into a liquid is called latent heat of fusion. If the amount of the solid is equal to 1 mole, then it is called the molar heat of fusion. The amount of heat energy required to change a given amount of liquid to a gas at constant temperature is called the latent heat of vaporization. If it's 1 mole of a liquid, then it's called the molar heat of vaporization. Next, we look at determination of enthalpy changes. We can be able to calculate the enthalpy changes for virtually all the types of reactions. We only need to know the mass of the substances and the temperature change. And then, enthalpy change is calculated as enthalpy change is equal to mass of the solution times the specific heat capacity times the temperature change. Let's start with molar heat of neutralization. This is the enthalpy change that occurs when an acid and an alkali react to produce 1 mole of water. We take 50 cubic centimeters of 2 molar hydrochloric acid and note its temperature. It's 20 degrees Celsius. Then we add 50 cubic centimeters of 2 molar sodium hydroxide. We notice that the temperature is rising, so it's an exothermic reaction. Note the new temperature and calculate the temperature change. So let's say when 50 cubic centimeters of 2 molar sodium hydroxide reacts with 50 cubic centimeters of 2 molar hydrochloric acid, a temperature change of 13.5 degrees Celsius is observed. Now, the temperature is measured in Kelvin, but a change in temperature will have the same value on the Kelvin and on the Celsius scale. So delta T will still be equal to 13.5 Kelvin. We can do it practically so that you can believe. The initial temperature is 20 degrees Celsius. On the Kelvin scale, it will be 293 Kelvin. Final temperature is 33.5 degrees Celsius. That is equal to 306.5 Kelvin. So change in temperature on the Celsius scale is 33.5 minus 20, which is 13.5. On the Kelvin scale, it is 306.5 minus 293, and that gives us the same answer, 13.5 Kelvin. So you see, you don't need to keep converting. Change in temperature is the same value on the Celsius and Kelvin scale. This is the equation for the reaction. The specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin. And so enthalpy change is equal to mc delta T. We start with the mass of water. The total volume is 50 plus 50, which is equal to 100 cubic centimeters. Because the density of water is 1 gram per centimeter cube, then 100 cubic centimeters of water will be equal to 100 grams. We convert that into kilograms, and that will be equal to 0.1 kilograms. So enthalpy change is equal to 0.1 times 4.2 times 13.5. That gives us 5.67 kilojoules. And because it's an exothermic reaction, we put a negative. This is the energy change that occurred during the reaction. But the term molar means per mole or for 1 mole. So how many moles of water were formed? We write the ionic equation. Only 1 mole of water was formed. So minus 5.67 kilojoules divided by 1 mole will give us minus 5.67 kilojoules per mole. And so the thermochemical equation will be as shown here. Next, we look at the molar heat of solution. We saw that when salts dissolved in water, a change in temperature occurred. We can calculate the molar heat of solution for ammonium nitrate. Let's say 4 grams of ammonium nitrate dissolved in 50 cubic centimeters of water. Temperature dropped from 20 degrees Celsius to 8 degrees Celsius. Enthalpy change is given by mc delta T. We start with mass. Volume of water is equal to 50 cubic centimeters. Density of water is 1 gram per cubic centimeters. Mass is equal to density times volume, so that gives us 1 gram per cubic centimeters times 50 cubic centimeters, and that gives us 50 grams. That is equivalent to 0.05 kilograms. Specific heat capacity is equal to 4.2 kilojoules per kilogram per Kelvin. Change in temperature is equal to 20 minus 8, which is 12. Enthalpy change is equal to 0.05 times 4.2 times 12. That gives us 2.52 kilojoules. It's an endothermic reaction, so it's a positive. That is the amount of energy absorbed in the reaction. But we need the molar heat. In other words, how much would it be if we had 1 mole of ammonium nitrate? We calculate the number of moles in 4 grams of ammonium nitrate. Molar mass of ammonium nitrate will be equal to 80 grams per mole. Number of moles is given by mass over the molar mass. That is 4 grams over 80 grams per mole. That gives us 0.05 moles. And so 0.05 moles absorb 2.25 kilojoules of energy. How about 1 mole? So 1 mole over 0.05 moles times 2.52 kilojoules, and that gives us 45 kilojoules. So the thermochemical equation is shown here. Next is the molar heat of displacement. Now, we know that a more reactive element will displace a less reactive one from the latter solution. For instance, zinc will displace copper from a solution of copper 2 sulfate. This reaction too is accompanied by heat changes. We can therefore calculate the molar heat of displacement. For example, When 4 grams of zinc powder was added to 100 cubic centimeters of copper 2 sulfate solution, the blue color faded away and the temperature of the solution rose from 21 degrees Celsius to 46 degrees Celsius. Calculate the molar heat of displacement of copper by zinc. Enthalpy change is given by mc delta T. Mass of the solution is taken as that of water. So 100 cubic centimeters is equal to 100 grams and is equal to 0.1 kilograms. Specific heat capacity is 4.2 kilojoules per kilogram per Kelvin. Delta T is equal to 46 minus 21, which is 25. Enthalpy change is given by 0.1 times 4.2 times 25. That gives us 10.5 kilojoules. Because it's an exothermic reaction, we put a negative. Let us now calculate the molar heat. We calculate the number of moles of zinc that were used. We had 4 grams. Molar mass of zinc is 65 grams per mole. So the number of moles is equal to 4 over 65, and that gives us 0.06 moles. And so 0.06 moles liberated 10.5 kilojoules of energy. How about 1 mole? So we have 1 mole over 0.06 moles times 10.5 kilojoules, and that gives us 175 kilojoules. Again, put a negative. The thermochemical equation is shown here. Now molar heat of combustion. We cannot be able to measure directly the amount of heat released during a combustion process, but we can measure the amount of heat transferred to, say, water during the combustion of, let's say, ethanol. Let's perform an experiment. First, we weigh the ethanol in container and record the mass. Then we note the temperature of, say, 100 cubic centimeters of water. In this case, it's 24 degrees Celsius. Put the burner under the conical flask and light it. We wait until the temperature goes up to about 45 degrees Celsius. The temperature is now about 44 degrees Celsius. We turn off the flame. Weigh the remaining amount of ethanol and its container. The difference is the mass of the ethanol that was used. With that, we can now estimate the molar heat of combustion of ethanol. Let's say we have the following values. Initial mass is 24 grams, final mass is 23.75, and therefore the mass of the ethanol that was used is 0.25 grams. Initial temperature of the water is 24 degrees Celsius and the final temperature is 44. Temperature change is 20. We calculate how much heat was absorbed by water. The assumption is that this is the same amount of heat that was released when the ethanol burnt. We are ignoring the losses of heat. So enthalpy change is equal to mc delta T. Mass of water is 100 grams, which is equal to 0.1 kilograms. Specific heat capacity is 4.2 kilojoules per kilogram per Kelvin. Delta T is 20 Kelvin. So enthalpy change is 0.1 times 4.2 times 20. That gives us 8.4 kilojoules. That is the heat energy that was transferred to water. And this is the same energy that was released by 0.25 grams of ethanol that burned. What if it was 1 mole? We find the molar heat. First, we calculate the number of moles in 0.25 grams of ethanol. Formula mass of ethanol is 46 grams per mole. Number of moles is 0.25 over 46, which gives us 0.005 moles. And so 0.005 moles evolved 8.4 kilojoules of energy. What if it was 1 mole? That is 1 mole over 0.005 moles times 8.4 kilojoules, and that gives us 1,680 kilojoules. Because this is the energy that was released by ethanol, and that this is an exothermic reaction, we put a negative. And this is the thermochemical equation. Next, we look at Hess's law. Now, a Swiss scientist, Germain Henry Hess, observed that the heat evolved or absorbed in a chemical process is the same whether the process takes place in one or several stages. This is known as the law of constant heat summation. Consider substance A being converted to B through this path, or A being converted to C first, and then C to B. Either way, A has been converted to B. According to Hess's law, delta H is equal to delta H1 plus delta H2. Hess's law is simply a corollary of the law of conservation of energy. It implies that the enthalpy change of a reaction depends only on the state of the reactants and products, and not on the manner by which the change is brought about. Consider the formation of carbon dioxide from carbon and oxygen. There are two ways in which this change can be brought about. A. Conversion of carbon to carbon dioxide. Or B. Conversion of carbon to carbon dioxide and subsequent oxidation of carbon dioxide to carbon dioxide. According to Hess's law, delta H is equal to delta H1 plus delta H2. Negative 393.5 kilojoules must be equal to negative 110.5 plus minus 283.0, and that is indeed true. Hess's law can be used in determining the heats of formation of certain compounds which cannot be synthesized directly from their elements. These include methane, ethane, sulfur 6 oxide, and others. For example, let us consider the formation of sulfur 6 oxide. Direct formation of sulfur 6 oxide cannot happen, but we can convert sulfur to sulfur 4 oxide. We can also oxidize sulfur 4 oxide to sulfur 6 oxide. With these two thermochemical equations, we can calculate the heat of formation of sulfur 6 oxide. Delta H is equal to delta H1 plus delta H2. Negative 297.4 plus minus 97.9, and that gives us negative 395.3 kilojoules. Now, consider the formation of methane. We cannot be able to measure the enthalpy of formation of methane. The theoretical formation of methane would be combination of carbon and hydrogen. However, if the reactants and products are burnt in oxygen, they will give us the same products. And therefore, we can be able to calculate the heat of formation of methane by considering the formation of water and carbon dioxide from the combustion of hydrogen and carbon given their heat of combustions as follows. The theoretical formation of methane from carbon and hydrogen would take this path. And then, the combustion of methane in oxygen would produce carbon dioxide and water. Combustion of carbon in oxygen will produce carbon dioxide, and combustion of hydrogen in oxygen would produce water. So whether you follow this path or this path, you will end up with the same products, carbon dioxide and water. And therefore, the enthalpy changes must be the same, so we can calculate the unknown. Path 1, that is delta HF plus minus 890, must be equal to path 2, that is minus 93.3 plus 2 moles of hydrogen, so 2 times minus 286. So delta HF minus 890 is equal to minus 393 minus 572. Delta HF is equal to minus 393 minus 572 plus 890, and that gives us minus 75 kilojoules per mole. And finally, we look at the relationship between the heat of solution, hydration, and lattice energy. In Form 2, we saw how sodium chloride dissolves in water. First, the sodium chloride dissociates into sodium and chloride ions. These ions then become stabilized in water due to the polar nature of water. So the process of dissolving involves 2 stages, and each is accompanied by energy changes. We start with a 3-dimensional giant ionic lattice. This structure interacts with water to such an extent that the solid dissociates into monoatomic gaseous ions which scatter in all directions. This process requires input of energy called lattice energy. It's therefore an endothermic process. The sodium and chloride ions then get surrounded by several water molecules in a process called hydration that releases energy called hydration energy. Hydration is an exothermic process. We can represent this in an energy cycle. The enthalpy of solution is the sum of the lattice and hydration energies. In this case of sodium chloride, the enthalpy of solution is given by 781, the lattice energy, plus minus 390, the hydration energy of sodium ions, plus minus 384, the hydration energy for chloride ions. And that gives us plus 7 kilojoules per mole. When experiments are carried out at a temperature of 25 degrees Celsius or 298 Kelvin and a pressure of 1 atmosphere, the values of enthalpy changes that are measured are called standard enthalpy changes. They are given the symbol delta H with a superscript theta. A subscript is also added to the symbol to indicate the type of enthalpy change involved